you probably have known him before as the primary author for Darngrim, the patch analysis tool. He currently works for Microsoft in their malware protection center, and we're going to talk about VM instrumentation. Yeah. So please give a warm round of applause.
Yeah, thank you. So actually, you can download the slide from this link. So if anyone is interested, yeah, you can just write down. Also, you can find this from the Shmoocon tag from the Twitter. So I just posted this morning, so you can find it. Okay, cool. So this is about AVM and AVM security and AVM instrumentation. So before that, maybe not so sure how many heard about AVM. So just one, anyone, two. So actually, this is the acronym for ActionScript Virtual Machine. So probably you guys all know about ActionScript, right? So this is the VM that will run the ActionScript bytecode. So to understand what AVM is, maybe we need to look into the format of flash file. So the flash file consists of header and tags. The header has some signature and version number, the length field, and it has tags. And the tags has individual data. It has a type, length, data structure. So each type has its own format. So from all the formats, one of the type is number 82. And this tag contains AVM2 bytecode. So not all flash files contain this tag, but some flash files that has some actions and some flash files that has been compiled with the ActionScript will have this tag. So what is AVM2? There are multiple versions of ActionScript, and the latest one is ActionScript 3, and AVM2 is that the virtual machine that runs ActionScript 3 bytecode. And the previous virtual machine actually used some kind of interpreter model. So every time the bytecode is run, it will interpret every instructions every time. So it was kind of slow. So they improved that using JIT. So probably you guys all know about JIT technology, right? So this is just-in-time compilation thing. So when the virtual machine reads the bytecode, it will actually dynamically generate the native code on the heap. So actually this thing sometimes creates some potential security risks. So there are some known vulnerabilities with JVM before. So JVM is much popular than AVM. So there were some known vulnerabilities before. So this is not only about AVM, but kind of AVM vulnerabilities are kind of very interesting. So the weird thing is that since 2010, we observed a lot of AVM2 attacks appearing from the internet. So that's very weird. So usually that was, all the attacks are caused by 1 byte fudging or that kind of stuff. So they don't understand much about that AVM, but they were doing just all those, 1 byte fuzzing, just changing 1 byte from the flash files and running it from the flash player. And if they observe some kind of crash, then they make some exploit out of that. So I'm not so sure they really understand what is going on, but they see some crashes and they make using some heap spraying and they make the exploit. And it was very, very successful. So the problem is that just like I said, all the software has the vulnerabilities, and this AVM is software, so virtual machine should have some vulnerabilities. And these vulnerabilities are not like a user. They are not just buffer flow, or they are not just heap overflow. They are kind of very, very complicated vulnerabilities. So just understanding the vulnerabilities are very, very difficult, actually. So, and debugging the vulnerabilities are not easy. So what I'm presenting today is about how we can debug these vulnerabilities that is not very user. So if the vulnerabilities are just buffer overflow, you can just debug it very easily, right? So the stack is corrupt, and you can just trace down what data is corrupting the data, and you can just easily figure out where the data is coming from. But for AVM, it's not that simple. It's all about some logical errors with the virtual machine cheat code generation thing. So to understand what is going on inside of VM, you need some kind of new method. And also, many malwares are actually using some kind of obfuscation thing to load the other sweep file dynamically. So probably you guys are very, very familiar with what is a JavaScript obfuscation thing, right? It's very, very popular, right? So whenever somebody is putting some link and you visit the site and you got owned, you will get owned. And in the case, actually, if you open up the HTML file, it's not plain text, just plain it's not plain HTML or JavaScript. It's kind of obfuscated itself. So kind of very, very in multiple layers of evil a method is called. So in that case, it is very, very hard to figure out actually what is going on under the JavaScript. So same thing is happening with sweep file. So in that case, maybe I will show you how we can use this AVM instrumentation to dynamically analyze all the sweep files. So all the methods are done with AVM instrumentation. And I'm going to show two methods here. One is code coverage investigation. And second one is hooking classes. So actually you can just hook some AVM supported APIs, and you can replace the API to your own. And in that case, you can just hijack every network traffic or some bytecode loading classes or data allocation classes. So if you hook the data allocation classes, you can hook all the memory allocation activities from the flash file. So you can see how it is allocating some heap memory, and you can see how they are using some kind of heap spraying from the AVM sweep files. So the first example is actually the vulnerability that was very, very popular last year. It was CV 2011-0609. This is kind of very, very most abused, one of the most abused vulnerabilities from flash files. So using this example, I will show you how we can use AVM instrumentation to trace how the code is executed. So with this example, I use trace API from ActionScript. This is some simple debugging API. So if you use trace API and put some strings and format related strings, then you can just print out some debugging messages to some debugging file. Also, maybe you can use debug file or debug line instructions from AVM. But this is same as what is with int3 instruction from x86. So if you put these instructions inside a bytecode, then it will call, it will check whether there is a debugger attached to the flash player, and it will actually call the flash player debugger. So if you download the Flex SDK, it contains the actually the flash debugger. So you can use this debugger for the flash file that is not intended to be debugged. So if you insert all these instructions to the flash file, then you can make it debuggable sweep file. So you can use the debugger to debug and trace steps through all the execution flows inside sweep file. But the first method is kind of enough to show how the code coverage is happening. So I use the first example here. So before that, we need to understand what is the CV 2011-0609 looks like. So the purpose of showing these vulnerability details is not to make you guys to understand what it is, because these details are very, very complicated. I don't expect you guys 10 minutes or something. So I'm just showing this to make you guys realize how it is complicated to understand and debug all these kinds of vulnerabilities. So the essence of these vulnerabilities is some instructions are created to work with object type A, and somehow object type B is passed to that instructions. So the GTA, the native code, is actually meant to be processing some type A object, and actually the control flow is actually passing some type B object to that, like a GT code. In that case, the type confusion is happening, right? So in that case, it's totally like processing some wrong object. In that case, it's like calling some method. When it's calling some method, actually it's accessing some data field maybe, and it makes like a call to somewhere in the memory that is not intended to be called. In that case, it will combined with heap spraying or G spraying, then it will make the code execution possible. So this is a diagram that shows what is happening. The left side diagram shows the original bytecode control flow. So if you can just open up all these bytecode using all the flash tools. There are a lot of flash disassemblers or decompilers. So you can just open up the original bytecode. So actually this attack file was generated from some valid, just normal C file from the internet. So the attackers just downloaded the file from somewhere. So they are just gathering some sample files, and they were doing some kind of 1-byte fudging. So they were just changing 1 byte and see if it is crashing. And they were just repeating them for maybe a few months or a few years. And they just found that if you just change 1 byte from this function, from the basic block B, so if you change just 1 byte from that jump instruction, you make that basic block to jump to between A1 and A2. So originally B was jumping to C and the C block, right here. The left side, it was jumping to C block. But if you change 1 byte from basic block B, it will make the jump goes to between the A1 and A2. It will split the A block, basic block A to 2, A1 and A2. So some kind of control flow, tweaking is happening here. So actually, if you look at the bytecode itself, this bytecode, this assembly was generated by some tools that our internal tool. So actually, we are using IDA, and we made some IDA plugin to disassemble all the bytecode. So left side is the original control flow. So this is kind of very, very abstract view, and this is the real disassembly from the real malware. So the left side is acquired from the original file that used for fudging, and the right side was taken from the malware. So if you compare the left side and right side, there is only one difference. So the B block was actually jumping to the middle block, some big block there. But if you look at the right side, the B block is almost same except the jump instruction. So the jump instruction is jumping to A2 block, just changing 1 byte. So new control flow is generated here. So you can actually dump all the zip code is generated inside the heap memory. So during the execution, actually, you can take out the heap memory and you can disassemble the heap zip code from IDA. And the view from the picture on the right side is the actual disassembly code from that G code. That is like generated from that original bytecode. So the original bytecode are generated like that form. So if you look at closely, they have some similarity in the form of the control flows and everything. They are not exactly the same, but there are some rules and a lot of optimizations happening there. So they are not exactly one-to-one match. But if you look at that, you can figure out, oh, actually it's calling some dynamic method from some object. You can figure it out. So this one is acquired from the original file, and this one is from the mutated file. So if you look into this, the left side is the original bytecode, and right side is the generated bytecode, generated native code, x86. So if you look into this, the actual form, the representation of the native code is kind of like changed a lot. Like if you compare this to this, just one control flow change makes the G code like a kind of like a messy or whatever. So actually this makes all the like a crash happening. So if you debug all these things from WinDebugger, you can see that actually the crash is happening inside the A2 dash block from the right side, the picture on the right side. So this is the summary of the vulnerability. So from the actual code was generated based on path B from this picture. So there are A2 basic block is getting 2 control flows, right? 2 incoming control flows, B and A1. Actually, the JIT code is generated from the path A there. So 8 code is generated based on the data type that is passed from basic block B. And the type is COM, green sock, core, simple timeline type. And A2 JIT code is actually processing that type. But actually when the sweep file is loaded, the control flow comes from A1. So A1 is passing totally different data type. And it makes the crash happening. And you can use this vulnerability to execute some like a code combined with heap spraying. So this is saying same thing. The actual code run is from A1 to A2, and this makes the crash. So to analyze all these vulnerabilities, so it can take a long time. It can take a few weeks, sometimes it can take a few days to figure out actually what is happening under the hood. So there are many shortcuts here, actually. The first one is sweep diffing. So if you have some malware samples, you can just look it up, open it up from IDA, right? So in that case, you can see some unique strings from the IDA files, the sweep files, because it will be using some component, some private component or some component from some website. In this case, it is COM, green sock, core, simple timeline. So if you observe these strings, you can just look it up from Google or Bing, and you can find some website that actually created that component. And in that case, you can just browse some website, and maybe you can find some similar original, like a sweep file. And using that sweep file, you can just comparing them, just using some like a hex diffing tools, right? Some kind of beyond compare, or there are some other tools that you can actually compare hex bytes. And using that tool, you can see what bytes are modified. And you can just disassemble all the sweep files, the original one and the modified one, and you can go to that position, and you can see, oh, the control flow is modified like this. So the output will be something like this. So after this sweep diffing, you can see, oh, the original control flows are modified to the mutated one. So you can just figure out, oh, maybe the jump instruction change, maybe making some type confusion here, and you can just guess that. And using combining that with some G-code dumping and like a debugging, then you can actually figure out this whole picture. And it takes a long, long time to perform all these things. And second method, the method, this is the actual crash you will get when you run the malicious sample. So from this, you can just see some native instructions, right? So it's moving some EDX70H data to ECX register, and it's accessing some invalid memory. And if you put some heap spraying shellcode to that memory, if you can load that using some sweep file like git spraying or heap spraying, then you can make the code execution happening. But from this picture, this crash point, it is really, really hard to figure out what is happening. If you can't find the original sweep file, then you don't have anything to compare, right? So if you have somehow you can find the original file, you can compare that to the mutated file, and you can figure out, what byte is modified, and what control flow is changed, and what is changed, and you can figure it out somehow. But if you can't find the original file, then there is nothing you can do much, right? So because the starting point will be this crash point, and there is nothing much you can do to figure out actually what is happening here. So these are the problems when you have some flash file crashing. It is extremely hard to figure out what is happening if you can't find any original samples. So the attack began maybe 2010 or maybe before. They just used some files from the internet. They just mutated it, and they just used it for the real attack. So it was really, really easy to figure out what was happening, because you can just search some unique strings, and you could find the original files. But these days, they make their own samples. So they find the crashes, maybe they do some more analysis, and they create their own POC file. So in that case, you can't find the original file because the attacker only has that original file. So in that case, it's very, very hard to analyze all these vulnerabilities. So to solve this problem, we can use code coverage testing. So this is the basic big picture that's showing how the binary instrumentation is done. So the upper picture shows the original sweep file. So it has a header and all the AVM. Different color means different AVM tags, different sweep file tags. And one of the tag is AVM tag, the yellow block there. So you can just dissect all the AVM, decompile or disassemble all these AVM tag content. And you can just insert your own instructions between them. So for all the functions or for all the basic blocks, you can just put your own instructions. In this case, it's a trace. You can just put a trace and some unique strings, each executing some basic block number or something, some unique numbers. So you can just insert all these instructions here, and you can just recombine all these instrumented AVM tag into one, and you create a new sweep file. So during this, the picture is very simple, right? So you just break it down, and you insert new instructions, and you just combine them all together, and you just run it.
Are you worried that by inserting these instructions, you will, for example, redo the way to keep this set up? So you're going to lose the original bug because maybe the heat-based bug that it's not constructed the same way or things like that?
That is really, really good question, because this approach. Yeah, the question was, doing this like a reconstructing thing, maybe the characteristics of the original bug might be lost, right? That is the question. So, yeah, actually that's why we are doing this. There can be other methods, like you can, actually AVM tag, actually you can just decompile them, and you can just get the original action script. And you can just put the trace instructions for every functions you want to trace, and you just compile them again, and you make the sweep file. You can do that. In that case, you will lose all the characteristics that is making the crash. So that's why we used this method, is preserving the original characteristics as much as possible. So it will not try to break the original structure of the AVM tags. Even though it looks invalid, we just try to maintain the original structures and maybe there can be some invalid instructions, and we are trying best to observe the original structure and instructions, bytecode and everything. So this is the disassembly from the original disassembly was instrumented like this. You can just put it is very simple, right? So it's calling trace method here for every basic blocks. So if you run this sweep file, it will generate a huge amount of log file. So it will dump the basic block numbers, and so that you can figure out, you can just grab these basic numbers from this disassembly later to see how the control flow is working. So this is the last part of that generated debug log. And if you look at the last line, actually the last line shows the point where the crash was happening. So to interpret that numbers, so it will show the basic block and 314.279 some numbers, and there is a 27. And 27 means the basic block 27. And actually you can exactly pinpoint where the crash is happening here. So basic block 27. And how about all these other numbers? So the other numbers are actually the function numbers and the basic blocks from other functions. And out of these numbers, you can figure out the actual call stack that is actually calling that exact function. So you can actually get the exact call stack. So it is coming from some, constructor from timeline max, and it's calling some classes and simple line timeline classes. And it's calling tweak-core constructor. So these all things, you can figure out, oh, this crash is happening when it is creating some classes. So this is the first example. So using this old tracing thing, you can figure out actually, oh, before using this tracing thing, what you get is actually this thing. So out of this thing, you can't figure out anything. But using this instrumentation, you can get actual exact call stack, and you can figure out what is actually happening inside that action script. And then the second example is the obfuscation thing. So just I said, AVM is used for obfuscate the sweep file itself. So you can actually, AVM provides, actually ActionScript provides the functionality to load sweep file, the other sweep file. So actually you can embed other sweep file inside the other sweep file. So you can, and it doesn't need to be in a bytecode form. So it can be dynamically generated using some instructions. You can just, so that you can't just take it out easily. So I will use class hooking to figure out how we can just dump the hex bytes like easily, even though it is generated dynamically. So many exploits use these things. Basically, every sweep file related exploits are using this method. And I will use CV 2011-06-11 vulnerability. This one is also very, very popular one. So the other one and this one is the most popular vulnerability from 2011. So this is the structure of the exploits. So they are usually delivered through some container. And the container file contains the layer 1 sweep file. And it contains layer 2 sweep file. So layer 1 is loading layer 2 dynamically. And actually layer 2 has some vulnerabilities inside it. So it will trigger the vulnerability. And the payload is generated from layer 1. So layer 1 will do all the G-spraying or heap spraying thing. And layer 2 will trigger the vulnerability, and it will make the code execution happening. And all these sweep files is just one sweep file, and it will be contained inside maybe PDF file, or sometimes it's Excel file, because there is no organizations that is allowing just sending sweep file to some mail account, right, these days. So they are just putting that inside some Office file, because you should allow Office files or PDF files. So that's why they are putting all these inside some containers. Or maybe you can just load these from some website. So you just put all these to some website, some sweep file, and just you pass the link and user clicks it, then you are just owned. So this is some picture that is actually showing how maybe, yeah, it can be very interesting picture, because I just got the idea when I was watching some documentary about World War II. So I was like very, very surprised. I was just wondering how to ignite the nuclear bomb. I was, maybe there can be very, very complicated method, but the method was like very, very simple. The nuclear bomb has some payload, right? Some nuclear materials. And the blue box contains the explosives, the bomb, actual some bomb, TNT or whatever. I'm not so sure. So I'm not like an expert in this field. So it has some explosives inside. And the blue box and the payload is connected through some pipeline. And there is a bullet inside the pipeline. So when the explosives are exploded, it will make like a lot of force energy, right? So it will make the huge velocity to the bullet. And it will make like a high-speed movement. And it will hit the payload, and it will make the all these nuclear thing happening. So this is same in sweep file. So layer 2 sweep file, it will trigger the vulnerability. So it will crash, it will make some embedded memory access happening. And actually that will just hit some heap spraying payload inside the memory, and it will make all the execution, code execution happening. So this is the most simple example that contains that layer 2 sweep file. So you can just open it from the, you can just open the sweep file from the hex editor and just look for FWS, because there is a signature for FWS file, right, sweep file. So if you read it in backward, it's SWF. So FWS and SWF. So just search for FWS or CWS, because they are the signature string for magic string for sweep file. So if you can find it, you can just take out that part to another file, and it is just sweep file. So you can just take it easily. This was happening like 2 years ago, but it's not anymore like this. So the other form is like using some strings. So push string is the instruction from AVM. So inside the AVM, it's pushing some like just ASCII string. So it's not in this bytecode form. But these are like just ASCII string. So you can just search for 465753, this string inside the sweep file. Maybe you can find these instructions or this sweep file, second layer sweep file. So this is saying same thing. So this is what is happening now, actually. So can you guys figure out what is happening here? So instead of pushing the string, it's pushing doubles and integers. Actually, double is 8 bytes, and integer is 4 bytes. So actually, if you combine all these bytes that is pushed to the stack, actually they are like they are actually sweep file. So they are splitting all the sweep file into like 8 bytes and 4 bytes, and they are pushing it to the stack instead of using that simple one-line string. So in this case, maybe they have some obfuscation, more obfuscations are happening there. So maybe it will be really, really hard to take out the original sweep file. So if you look down, actually it's using some kind of encryption method. So here, so it's calling encrypt. Actually, what it is doing is decrypting or decoding, but they are just using wrong name here. So it is the string that is pushed to the stack is not actually the sweep file itself, but it is in kind of encoded format, kind of using XOR or whatever. So it's calling encrypt, and after that, actually it's loading here, load bytes here. So it might be so small. So it's load bytes. So it's pushing everything to the stack, and it will decode using decode the thing using their own algorithm, and after that, it will load that to the memory, dynamically load it. So this is the routine that is actually doing the decryption thing. The name is encrypted, but it's doing decoding thing. So it's just calling here. It's pushing 0xFF, and it's doing XOR. So it's XORing the original like data, and it will make the original sweep file data. So the method might be you can just insert some dump code between these load bytes part, right? So if before calling this load bytes API, maybe you can just insert some trace method and make it to dump all the hex bytes. But there is another like method here. So this one is much better. So you can use some AVM insertion. So you can create your own AVM code, and you can insert it to the malicious code and make the original malicious code to call that AVM. So this is the method using some inserting. So you just insert some dump method there and make it to dump the hex bytes. So it involves all the stack level calculation because this AVM is using stack. So maybe if you don't process the stack correctly, then maybe it can mess up all the things and it will make all the things not working. So you can just hook the class. And I'm using AVM insertion. And one more method involved with this is whenever the AVM is loading other classes, it's using names, actually. So it's a string. So if you replace the original string to your own class's name, then you can hook up all the calls to the original class. So you just need to make some stub code that is calling the original one, and you can just load it to the original sweep file and make all the calls to that original class, make them go through your own class. So it's a kind of detouring or like a class hooking thing. So this is very, very simple in AVM world because it's using classes, not kind of some fancy table or whatever. So it's just a string. So you just need to replace the class name. So this is some concept from biology. It's a kind of very, very simple concept, right? So there is chromosome A and chromosome B on the left side. And chromosome A has some feature that is very, very good. So you need to, for example, if there is corn and it has some bugs are eating the corn. And chromosome A has some like the genes that makes some like